Hi, I'm Lynn Jones. This talk is intended to give you an overview of the survey strategy for the Rubin Observatory Legacy Survey of Space and Time, the LSST. This should be an introduction, high-level overview of the high points of what we're talking about with the survey strategy. So, for starters, the LSST is a 10-year survey to be carried out by the Verisi Rubin Observatory. Rubin Observatory has a 6.5 meter primary mirror and a 9.6 square degree field of view. The telescope is located in Chile, so this is a southern hemisphere survey. The primary science drivers for the LSST are to inventory the solar system, map the Milky Way in local volume, explore the optical transient and variable sky, and constrain dark energy and dark matter. In the course of doing so, we'll catalog about 5 million small bodies throughout the solar system, 10 billion stars, 10 billion galaxies, and have about 800 plus observations per pointing. In order to meet these requirements and satisfy these science drivers, we need lots of area, lots of visits, multiple band passes, and well-calibrated photometry and astrometry. The very basics for these are spelled out in the LSST Science Requirements document, the SRD. And these basic requirements are to survey 18,000 square degrees with 825 visits per pointing over that 18,000 square degrees. The photometry and astrometry have very strict requirements for calibration that primarily drive how we distribute the visits over the entire lifetime of the survey. The survey will be carried out in UGRIZY filters, and these are chosen both for stellar population characterization and also for measuring the photo-Z's of all those galaxies. So the basic survey strategy, one of the primary questions is how should we distribute these 10 years of visits around the sky? The SRD spells out 18,000 square degrees must be covered, but it doesn't say where. This 18,000 square degrees is the wide, fast, deep primary survey area. This is what gets most of the visits for the survey. We need a large area with low dust extinction for extragalactic science, coverage of the ecliptic plane for solar system science, the galactic plane and the LMC, SMC for mapping the Milky Way and transient and variable science, and the southern celestial pole helps continue that mapping of the Milky Way. Altogether, that encompasses more than 18,000 square degrees, but the SRD spells out 18,000 square degrees must get 825 visits per pointing. Now, it doesn't say anything about the timing of those 825 visits, so that's another survey strategy question. The deep drilling fields are a subset of pointings. There are 5 pointings that have been announced, and we have a commitment to observe at least 1 magnitude deeper in these deep drilling fields than in the wide, fast, deep. The idea is they serve as calibration fields, and also that they get a much more rapid and deeper cadence. The rest of the time for the survey, how should we spend that though? Because to cover 18,000 square degrees with 825 visits requires at least 70% of the total LSST available time over those 10 years, but it doesn't require all of the time. But remember, we did say we had more than 18,000 square degrees that should be covered for our basic science. So where should we distribute the visits? This is one of the primary questions. If we set up the wide, fast, deep, that primary survey area, our initial version of these visits, this footprint, was to distribute this across a relatively low air mass range, and this is the baseline version here. Then we added extensions in the baseline to cover the northern ecliptic spur, this is to capture those solar system objects, the galactic plane for transient and variables, and the south celestial pole, again to help with mapping the Milky Way. But for extragalactic science, we might prefer to move that wide, fast, deep footprint to a low dust extinction area only. So in this case, you pull back from the galactic plane and then extend the wide, fast, deep area north and south so that we still make 18,000 square degrees. This is what we call the big sky version rather than the baseline. We still need northern coverage, so we add visits in the north. In this example, we've added visits in a ring around the north, but you could just have that bump around the northern ecliptic spur. We have the galactic plane coverage, and in this case we've added more intense coverage through the bulge to do a much better job at capturing the transients and variables within the galactic plane. And then we still have celestial pole coverage. One thing you might notice is that overall we've extended our sky coverage here, and so we actually have fewer visits in the wide, fast, deep, but it is still meeting that 825 visit per pointing minimum. In both of these simulations, you can see that these deep drilling fields pop out as places that get many, many VORP visits. In both of these simulations, we've kept them the same. And then in the last question is how to distribute these visits over time. We might take our 825 visits and just distribute them uniformly over time, or we might split them up, split the sky up into different areas and cover them in different, sort of shift the focus around so that we have, if we have 2 declination bands, in one year we might focus on one part of that band, the northern sky or the southern sky, and then in the alternating years, sort of flip that. We might split the sky up into 3 declination bands or 6 declination bands. The idea here is to explore the idea of rolling cadence where we shift that focus around the sky. You could then increase the cadence during the period that part of the sky is in focus at the cost of decreasing it during the rest of the time. So, survey strategy overview. High points are what should the survey footprint look like, and in particular what should the wide, fast, deep, northern ecliptic spur, galactic plane, and south celestial pole coverage look like, and how should the distribution of visits be between the different filters in those footprints. How should the visits be arranged in time? So the rolling cadence, but we might also look at the cadence within a night or a season and the visit exposure time itself. What should the deep drilling field cadence be and how much time should they receive relative to the wide, fast, deep? And what about other mini surveys? If we have time available, can we do short exposures over the entire sky, add a twilight NEO mini survey, add high air mass observations for DCR? So these are some of the questions. The primary thing you should take out of here is what the footprint looks like and generally how we're putting visits on the sky.